like to start this afternoon competition. I'm Jen Chen from the National Taiwan Ocean University. So maybe we introduce our jury first.
I'm Li Zhongxin. I'm from Donghai University.
National
Taiwan University.
So please each team introduce yourself first. Reporter. Over there.
I'm the captain from variable 1, and I'm Yang Yongyi, case Gary Tong, 陈耀启，侯文新，陈轩慈。
So opponent.
是人，那个中文题目对，是等于是那个观察者。
So, okay, I'm team leader of Team Bernoulli, and my name is Tong Weizhe. And he is Liu Jiachen, Liang Liyun, Chen Jianchang, and Nan Guozhi.
So now opponent has 1 minute to challenge the reporter the problem.
Number 11.
Accept.
Accept. Okay. So have 1 minute, 5 minutes to prepare your slide. Please, all of the presenter write down your name on the board. Okay, reporter, the stage is yours. Stop.
Hi everyone. Today I'm going to report question number 11, screen hysteresis. I'm the reporter from variable 1, Chen Xuanzi. And here's the problem statement. We connect two identical linear screens symmetrically to a mass in a V shape and apply an adjustable force to the mass. When this force is varied, the resulting motion of the mass depends on the history of the changes in applied force under certain conditions. Investigate this phenomenon. And our experimental directions would be applying an adjustable force to an object, and the phenomenon of hysteresis is studied by measuring the position of the screens and at the equilibrium. So here's our system looks like. So this is the mass, and this is the screens. And next is the phenomenon. So here, we observe the phenomenon from this simulation. So this is the mass, and this is the screens. So from the observation, we can find out that when the force is the same, however, the mass position is different. So this is the phenomenon of hysteresis. And so next, we analyze the force. So the resultant force equals to the external force minus the elastic force. And so here, next is potential energy. So potential energy equals to the negative work done by the external force and plus the potential energy of the two springs. And then, what is hysteresis? So hysteresis refers to a state of a system which is not only related to the input of the current system, but also has different results due to the different path of its input processes. So it is influenced by its historical state. So the relevant parameters of our experiment would be external force, the horizontal distance of the springs, and the vertical displacement of the spring, and the natural length of the spring. So next, first is our numerical simulation. So we're going to find the possible equilibrium configurations. So first, we discuss the x, which is the horizontal distance of the springs. So this is a fixed value in the problem statement. So we're going to find the suitable x. When the resultant force and the external force both equals to 0, we're going to find the relationship between the x and the y. So here, when the resultant force and the external force both equals to 0, there might be two conditions. The first one is it's y equals to 0, or is this equals to 0. So we can get that x and y form the equation for a circle with a radius of L0. So here's our code. We use Python to do the numerical simulation, and we discuss our second situation, and then we calculate and plot the graph. And so here's our result. So in our graph, the x-axis is x, and the y-axis is y. And here, when the external force equals to 0, when the x is bigger than L0, there's only one possible equilibrium. And however, when the x is smaller than L0, there are three possible equilibria, and two of them are stable, and one of them is unstable. So to find the hysteresis phenomena, we use the x smaller than L0. And this is our next numerical simulation. We're going to find the numbers of equilibria when changing x. So our purpose will be bringing the different values of f. While other parameters stay constant, we observe the relation between the resultant force and y. And this is our equation from our theory. And so here we also use Python according to our equation to bring y to solve the resultant force. And here's our code. We define our equation and bring values and plot the graph. So here's our result. The x-axis is y, and the y-axis is the resultant force. So here, each different color line, they stand for a different external force. So when we zoom in and see, this is when the resultant force equals to 0, and also when the time that is at equilibrium. So we can see that different external force, they have different intersections with the resultant force equals to 0. So we are going to find the critical value of f when the intersection goes from 1 into 3. So here, when the resultant force equals to 0, we solve y and then give the value of y at each of these turning points. So this. And here, the corresponding values of f minimum and minima using the y smaller than 0, and the f maximum at the maxima, which is y bigger than 0, can then be evaluated into this. And so here, in the conditions that the f maximum equals to 0, and that's the moment when the f equals to f1, and when the f minimum equals to 0, when that's the moment when the f equals to f2, the equation would look like this. And the critical value of f we get from our parameters is this. And so next is our discussion. And we look at the same graph again. So the x-axis is also y, and the y-axis is the resultant force. So here, the orange one is when the external force is smaller than F1. There's only one possible equilibrium, just like here. And when we look at the green one, which is the external force bigger than F1 but smaller than F2, there are three possible equilibria, and two of them are stable and one of them is unstable. And when we look at the external force bigger than F2, there's only one possible equilibrium. So here's our conclusion. So hysteresis may occur when f is bigger than f1 but smaller than f2. So there are three possible equilibria. And this is our next numerical simulation, which is hysteresis. And our purpose would be apply an adjustable force to an object, and the phenomenon of hysteresis is studied by measuring the position of the springs and at equilibrium. So while other parameters stay constant, we observe the relation between F and Y. And we also observe this while the Newton force equals to 0. So here we also use Python, and according to our equation, and we bring in the Y to solve the F. So here's our code. We define our equation and then do the calculation and plot the graph. So here's our results. So in this graph, the x-axis is the external force and the y-axis is the y. So here, the solid line stands for the stable equilibrium, and dashed line stands for the unstable equilibrium. So you can see that there are 3 possible equilibrium while in this range. So this is our discussion. So imagine starting out from f smaller than f1, just like this, in this range. So it stayed at the lower stable branch. And when you look at the system, it will look like this, in a V shape. And however, when we keep increasing f, and now f is bigger than f1 but smaller than f2, and it will still stay at the lower stable branch. And this is a characteristic of a stable equilibrium point. So this causes the system to remain in the vicinity of the previous state. So this is why it don't go up to here or here. And when you look at the system, it will look like this. It's also in a V shape. And next, when we keep increasing f, and now f is bigger than f2, just like this, it stays at the upper stable branch, and it will look like this when you look at the springs. And then we decrease our f back. And now f is smaller than f2 but bigger than f1. However, this time it stays at the upper stable branch. And this is also a characteristic of hysteresis. So it would look like this. And step 5, we keep decreasing f, and now f is smaller than f1, just like this. It will stay at the lower stable branch. It would look like this in a V shape when we look at the system. So here we're going to discuss the potential energy and the phenomenon we observe. So we use GeoGebra to visualize the potential energy, and this is the equation we get from our theory. And here's the discussion. When we're starting out from f smaller than f1, there's only one possible equilibrium. And when we look at the potential energy graph, and the x-axis is y, and the y-axis is the potential energy. And here, with the lowest part of the potential energy, this is the place where is the equilibrium. And so next, when we keep increasing f, and now f is bigger than f1 but smaller than f2, there are 3 possible equilibria in this range. So this is the potential energy of this part. And here, there are 3 possible equilibria at here, here, and here. And 2 of them are stable, and 1 of them is unstable. And for the step 3, we keep increasing f, and now f is bigger than f2. There's only 1 possible equilibrium, and this is how the potential energy looks like. And this is the equilibrium position. And now we decrease the f back, and now f is bigger than f1 but smaller than f2. There are 3 possible equilibria, and 2 of them are stable and 1 of them is unstable. So it would look like this, and the system will stay at the lowest part of the potential energy. And so here, when we keep decreasing f, and now f is smaller than f1, there's only 1 possible equilibrium now. So it will stay at the lowest part of the potential energy. So our conclusion would be, when the f is bigger than f1 but smaller than f2, there are 3 possible equilibria, and 2 of them are stable equilibria, and 1 of them is unstable equilibrium. However, the potential energy is different due to the historical input. So it might look like this or look like this. So the conditions under which hysteresis occurs is the system enters the critical value twice from outside the critical value. So you can find the hysteresis. And next is our conclusion of every experiment. So in the first, in first experiment, we said when the external force equals to 0, when the x is smaller than L0, there are 3 possible equilibria. So we use this to find the hysteresis phenomenon. And for the second experiment, we change f, And we find out that the hysteresis may occur when F is bigger than F1 but smaller than F2. And we also find the equation of how to get the critical value of F. And for the third experiment, we know that the conditions under which hysteresis occurs is when the system enters the critical value twice from outside the critical value. And here are my references. My report, and thank you.
Can you please turn to page 5? So, is your simulation work in 2D world or 3D world?
2D.
2D. Okay, and please turn to page 14. Can you explain the formula and where it comes from? The formula.
This is the resultant force, and this is the external force, which includes gravity. And these are the elastic force from the Q screw.
And how did you get this formula?
You analyze the force, and you can get this formula.
Okay. And please turn to page 17. Can you explain how this code works and how you got input and get a result?
What do you mean?
The code. How you gonna simulate all the phenomena?
We write Python and we put our equation into it, and we define our equation into that.
Did you have the value of the potential energy?
The value of the potential energy.
Yes.
You mean I didn't get the real value, and also it will change while you change all the parameters.
Okay. And did you did an experiment?
No, because we think the numerical simulation is enough for this.
And how you gonna make sure the simulation is right?
The result is
So 2 minutes times up. You have 3 minutes to prepare
Okay, hi, I'm Corners from Team Music, and my name is John here. Today I'm gonna okay, and the reporter, they use code to explain their phenomenon and in 2D words and they use the simulated code to make sure their formula is right. And they also use the decimals to get a potential energies formula. But they didn't do the experiment, so I still don't know if their simulation is right. So, and because they didn't do the experiment, so we cannot get the result of this phenomenon. But from simulation, we can get a fastless result, and their parameter is the length of x. So, okay. And now I'm gonna invite the reporter to discuss about their report. So how will you do the experience if you to support your simulation data?
We think we don't have to do the experiment because it is very hard to do in the real life. Because when you are trying to do this experiment, the spring it bends, or maybe it would move in the z-axis. So it would be very hard for you to get the data.
Then you can change your simulation to a 3D world, and then 3D, and then you can do the experiment to support your simulation data.
But because of the quasi-static manner, so it would always stay in the two-dimensional. So we don't have to do the 3D simulation.
Okay. So can you please turn to page 42? Right. And how to get this chart?
Oh,
How to get it?
we get this chart from this. So we remain other parameters stay constant. And we observe the relationship between the external force and the vertical displacement of the screen while the resultant force equals to 0. And we use the Python and we get this chart.
So you use a Python to get this chart?
Yes.
Serious? Okay. And have you tried to have the videos of the simulation?
Yes,
video?
we have that. So this one.
This one?
As you can see, when we increase the force, the screen goes from extension, then it goes into compression, like this, into the orange one. And it goes from the inverted V shape. And then when we keep decreasing the force, and it goes from extension into compression, and goes back to the V shape.
And you go back to the vision. Okay.
Yes.
So you think he will affect the result?
Can you say that again?
The thinking, this one.
The screen.
Will it affect the result of the experience?
Yes, it would affect the K, which is the elastic coefficient in our.
So did you do a simulation of it?
What do you mean?
So did you do a simulation of K, the value of K?
Because this is a numerical simulation, so the K value, we can set the K value into any value we want. So, yeah.
So you say you do a parameter at the x and right? The x.
Yes.
So what do you set the x in the same value but change the k's value? So can you get another chart for this?
Yes, we can get that, but we didn't do that because we don't think that is important in the hysteresis phenomenon.
Is it important?
No, we don't think it is
So
important.
using the X, it affects more than the K, affects the results.
I think they cannot be compared because they both affect the result. Yes, and also the X is a fixed value in this experiment.
So, can you please change the page 25? 25. So, as the X, as the Y.
Can you say that again?
Y.
No, that is just a line to help you to see this graph.
And what's this Y?
Oh, the unit of it is meters.
Meters.
Yeah.
Okay. So, can you please turn to page 37? So, how do you find fix X?
Oh, how did I get fixed that?
Fix X.
Oh, we can choose the suitable X, which we get from our first experiment. The X, when the X is smaller than L0, and it will be suitable. So we choose an X. And here's the parameters we use in our experiment. This. And this is the parameters we use while in our simulation.
This?
Yes.
Okay. And please turn to page 42. And you have a video, please? The simulation video.
Oh, you mean this?
Yes.
This is the same as the observation video.
And did you add the force into this system?
Yes, the F is the external force which includes the gravity. So we change F during this whole process. We change it from smaller than F1 into the F bigger than F2. And then we decrease it back to F smaller than F1.
So, then please turn to page 10, that's the potential energy.
Here.
So, I think the potential energy will affect the
Not the potential energy affect the experiment, but we can get different potential energy graph during the experiment. And we did that in our last experiment. So we compared our result and the potential energy graph.
and please do page 20. And how you can explain the formula and how it connects to the simulation or the
Oh. So here, this is our original equation.
yes.
And so here, we want to get the critical value of F. So when we differentiate our equation, we can get that y equals to this. And then when we bring y into our original equation, we can get these two.
So you solve the y and
Yeah.
so how you can calculate the f.
Calculate the F.
F.
Oh, we use Mathematica. Yes. So the computer do the calculation. So it is correct.
So you show the so you use the formula so you input the formula to the computer and you will get the answer of the S.
Yes.
how you gonna put this in the real world?
Put this into the real world.
Yes, bring it to the real world. So this is the same of the real world situation.
No, it won't be the same because the real world it is very hard to do the hysteresis phenomenon. So we do the simulation.
So you do the simulation, but is it in the real world?
Yes, because real world you can't get the phenomenon. It's very hard because the spring might bend and many factors affect that.
Is that you just said it's right? So wait.
And also and one more reason that we do the simulation is because we have to keep that in every moment the resultant force is equals to 0, and which is the quasi-static manner. So that our experiment result will be accurate.
Okay, so we're gonna use the 2D simulation to get the results and bring it and use the results to the experience to the real world situation. How? Yeah, because you guys only do the simulation, but I can understand why this can use in the real world.
Yes, I mentioned that because the spring might bend in the real world, and also we have to keep every moment the resultant force equals to 0, so it is stay in the quasi-static manner. So the result so that the result will be accurate. Or you do in the real world, the result won't be accurate.
Okay. And this is all my questions.
Thank you.
So, report.
So I asked the reporters how they can put the simulation data into the real world. So they say because the experiment is hard to do it, so they didn't do the experiment. But they don't have the data to prove their theories and their formula is right. They use formula to get a data, but they didn't use the data to get a formula or to improve the formula is right. And they use tons of simulations and theory to get the conclusions, and but the results may different from the real world because it's a simulation, it's not a real world, and this is all my conclusion.
Okay, review.
Okay, hello, I'm a reviewer from TYPT, and the first question I want to ask is about why it will happen the hysteresis. Yes, why it will happen.
This is the phenomenon.
Okay, and about the how about the
Sorry, can I say more?
the
And you can see that in the potential energy graph. Potential energy graph over here.
and about the why it will happen hysteresis.
Seriously, you mean what?
About the problem statement.
Can I say it first?
Yes, also.
So when you look at the potential energy graph, you can see that there are 3 spots that the slope is equals to 0, and that's the place where the equilibrium is.
Okay, and what do you think about when it will always happen when the spring is at V shape and it will happen hysteresis, or other shape also happen?
I think it might only happen in V shape.
Okay, and how about
The first question you asked me is the first question.
okay.
You said it has the force, and if it has the force, there will be some potential energy to cause this phenomenon.
And second question.
Can you please say?
Will the hysteresis always happen when the spring is at V shape, or other shape, or always will
I
happen?
think only in the vision.
Okay, and about the problem statement, what's your definition of history?
So the hysteresis is when you input a value. However, there will be different results from there will be different results because of the historic input.
Okay. Well,
I think if you put first exam, you can get the same result.
okay, and can you turn to the page 18? And I want to ask why at 1 stable point and 3 stable points. Why were 1 or 2?
We'll look at the potential energy graph. Because here, there's only one spot with the slope equals to 0. And when the step is in the critical value range, there will be 3 spots that the slope equals to 0.
Page 26. So, and about the opponent, and what do you think why as the report shows the picture, the middle part like this, the middle part at where the stable is stable. Why?
Time's up.
Maybe. Hello everyone, I'm the reviewer from Team Bernoulli, and today I'm going to review number 11, spring hysteresis. And our statement is connect to identical linear springs symmetrically to a mass in a V shape, and apply an adjustable force to the mass. When the force is varied, the resulting motion of the mass depends on the history of changes in the applied force under certain conditions. So investigate this phenomena. And so about this report, the theory he used is force analysis and reason of the hysteresis and the equilibrium points, also the maximum force and the minimum force. But I think in his experiment, he didn't do the experiment, but he used the simulation to predict the result, and he used different horizontal distance and F1, F2 calculation in equilibrium amounts. And about the strength, he using Python to simulate the conditions, and he compared the simulation and also showing the explanation of hysteresis. But his suggestion is that he should combine theories with the experiment data, and also, but he didn't do the experiment. So, and the data's explanation can be more clearly, and also show the video to explain the problem more clear. And also, he should do a real experiment to measure the simulation. And about the opponent, he asking about some detailed point of the experiment, and also he asking the axis of graph. And about the suggestion, I think he can add more detail in the theory and also what means of the equation to do with the data. And also he can ask more about the formula and in the simulation. And And about the missed point in the discussion, I think that you should discuss the properties of simulation and the reason of why happened hysteresis in the energy process and F1, F2. And about the discussion, the opponent asked the reporter that how do you get the equation of F1, F2? And then he said he used simulation, and I think he can show the original equation to see how he simulated it. And also the second is X more important than K. And the reporter said not important, and I think he should compare with it because it's different parameters. And third is how to calculate F. And the reporter said he using equation, and I think he could show where the equation from and also how to calculate it. And about the experiment and how to do the experiment in real life. And he said hard to do, and because the spring will bend, but he can maybe fix on the same surface and also try to perfect situation of the spring. And the second is how to use, and the reporter said adjust the parameters. And third is do you add force in the system, and the reporter said he adjust the parameters. And about what I asked, first question is what caused hysteresis? And the reporter said 3 points, and I think different energy in different equilibrium points, like the stable point will affect. And second is why is 1 stable point and 3 stable point, and it's a different hysteresis, I think, and this from the delta energy. And third is definition of hysteresis, and I think it's happened because the energy lost. And also I asked why V-shape have relationship to the hysteresis, and he said reporters and opponent also said yes, only V-shape will happen the hysteresis, but I think he should consider more shape of the spring to simulation or do the experiment to compare with his data. That's on my review. Thank you.
So, a reporter, you mean?
So here's my concluding remark. So first, we want to clarify the definition of hysteresis. So the opponent, they mentioned that they think hysteresis, when we input a value, there will be the same result of the system, but that is not hysteresis. And the reviewer said that this is caused by the energy loss, but that is not the reason of the hysteresis at all. So the hysteresis is when we input the same value. So the different paths of its input processes. So it will be influenced by the historical state. So when you input a value, the result might be varied. And so here's our concluding remark. And first, we have to explain why we didn't do the experiment in the real world. So the reviewer and the opponent, they both suggest me to do in the real world. But when we're discussing the hysteresis, we have to keep that everything is in the accurate control of the external force and make sure the result force remains always 0. So it would happen hysteresis. And also the opponent asked about changing K or L0. But our main focus is changing the force as the problem statement. And also, they asked about potential energy. The potential energy diagram can help us visualize the equilibrium positions and numbers. And for the critical F, the differentiation of equation can get the value, so with knowing the equilibrium numbers. And also, the reviewer, he asked about the page number 18. So he asked why would there be more than one possible equilibrium. So this is because from our theory, we can know there are 2 possible conditions, and one of them is y equals to 0, and one of them is they would be like the radius of L0.
So question from the jury. Any questions?
Reporter, you say the real world is too difficult to do experiment. But have you ever tried?
Oh, we've tried, and we failed.
You failed.
Yes.
And opponent, did you try experiment? Do you think it's very difficult?
No, I didn't try experiment, but I think yes, it will be very difficult, but you can do it. But yeah, okay.
好吧，我记得you try the experiment.
Yes.
Is it easy or difficult?
I think it's not very difficult because I try to use the same flow rate and the little flow rate to drop the water, and the force will be increased slowly, and so maybe the bending will not very big.
In the problem statement, it's stated clearly, you should study the resulting motion of the mass. Motion. Now, from your report, I don't see you study the motion. You only study the steady condition, right? Is that right? Next, to all of you, the hysteresis, it should be related to, say, the spring constants. That's material properties. And isn't that correct? The hysteresis should be related to the spring constant of the spring used, because that's your physical system, and of course the weight. So, what's the what do you answer for it? Shouldn't the hysteresis be related to the spring constant, and not just the strength of the force? Because that's bifurcation, that's not hysteresis.
I think it should relate it to.
How about the reporting?
Of course, it relates.
Of course, but you chose not to perform any experiment, and you fix your K like it's an ideal spring. I think that's probably not what the problem is asking. The motion and the hysteresis. But what you describe is actually whole bifurcation things. You know, you should study the motion. And when you say, shouldn't that be also doing this problem that you compare theory with experiment? When you say stable, you should show us your experiment show it's stable, it's oscillating somewhere there. Should. I'm happy because you understand.
So I have the.
Okay.
No.
I think all you say that the two-dimensional motion is enough. But when you pull the spring sideways, the role placed by the gravity is different. It's different. So that should be studied. I think that's also included in the problem. It deliberately not stating in either it's one-dimensional, two-dimensional, three-dimensional. And I think that's open. Sure.
Okay, I have no comment on this. Oh, but the time is for the jury for the score.
You were one of the jurors. We don't have any. You were wasting our time.
Okay. I have one. So have you studied the when you talk about the V shape, this always a symmetry V shape, or you also can study the other kind of the asymmetry V shape, like the Professor Tsai mentioned about. But because you do the simulation, I think it's quite easy to simulate that one.
It should be quite easy. With simulation only, without experiment.
Okay, time's up for the score for the reporter. 6, 5, 6, 6, 5. Oh,
Oh, you're, okay, that's
okay. So scroll for the component. Six, 5, 6, 7, 4. The scroll for the reviewer. 8, 7, 6, 6, 7. Okay, we have the 15-minute break.